Alrighty, nerds, welcome back from our extended hurricane break that we had all of last week off. Good news is that the hurricane happened in the middle of material that's supposed to be review, transformations, right? Hyovas, reminding you, Hyovas, my favorite transformational word, horizontal, inside, opposite, vertical, outside, same, just describes to us how changes to our functions affect what the graph looks like. So here, you had two transformations going on the outside. So those are vertical because they're outside. And there's one on the inside, so one horizontal. Outside changes because they are the same as what we expect will follow PEMDAS. That means multiplications happen before additions and subtractions. Wait, do you want to staple that and hole punch it? You can. It's right there on the corner of the desk. Just watch that hole puncher. It'll school you. Make sure that it's actually in the little metal deals. So anyway, so this is reflect over x-axis and then shift up 4. This looks like it's taking 2 away from your x's. Horizontal, inside, opposite. It's actually adding 2 to your x's. So this is shifting to the right 2. I would like to remind you, though, that AP is not ever going to give you a direction for a shift. They're not going to say up, down, left, or right. Instead, they'll use positive numbers and negative numbers. Did a hole punch correct? Yeah. Okay, cool. So we won't say shift up 4. We'll just say vertical translation 4 units. If it was down 4, it would be vertical translation negative 4. Okay? Speaking of, hey, look, right there. So I'm going to try to keep it the same colors. I have 2 outside transformations, and outside transformations, vertical, outside, same. Follow the order we expect, so they will follow PEMDAS. That means we're going to have to deal with our multipliers first, then our addition and subtraction. So what do we have? We have a vertical dilation, factor 2. Remember, you don't have to say stretch or shrink. Just say dilation for everything. Is that a stretch? Yeah, it is. So that's going to make the graph look taller. But you could say vertical dilation factor 2, and then vertical translation of negative 4. I don't know if it makes sense to say negative 4 units, so I'm just going to say negative 4. Okay? That means shift down 4. That's what that means. And going on the inside, I only have one transformation here. So this is going to be horizontal dilation because all addition and subtraction is, not dilation, excuse me. All addition and subtraction is translation. So horizontal translation, remember, horizontal, inside, opposite. It looks like I'm adding 3 to my x's. I'm not. I'm subtracting 3 from my x's. So that is a horizontal translation of negative 3. Which means shift left 3. But you'll never see the words up, down, left, or right for translations. Okay? Our parent y equals x squared graph is the same black dotted one that's here. So it goes through 0, 0, 1, 1, 2, 4. And then it's those reflections. And go through them as a dotted graph. So there's the parent function, y equals x squared. Now we're going to graph this one. Okay. It's in vertex form. What makes the inside equals 0, comma, the number to the far right will be the vertex. Negative 3, comma, negative 4. Negative 3, negative 4. And then you could just plug in points if you want to. So I would go 1 to the right at negative 2. Let's see. Negative 2 plus 3 is 1. 1 squared is 1. 2 times 1 is 2. And 2 minus 4 is negative 2. So negative 2, it's reflection. And then plug in the next x, negative 1. Negative 1 plus 3 is 2. 2 squared is 4. 4 times 2 is 8. 8 minus 4 is 4. 1 comma 4. Negative 1 comma 4. Did I do that math right? It feels weird. Yeah, no, it's good. And then its reflection then is way up here. This graph looks skinny, doesn't it?
Yes.
It's not. It's taller. And I could prove it. I could prove it. These were the first pretty points away from my vertex, right? See how they're only 2 away from each other, left and right? Look here. The corresponding pretty black points were also 2 away from each other, left and right. Here, these pretty black points were 4 away from each other, left and right. And the corresponding blue points are still 4 away from each other, left and right. But the vertical distance from here to these 2 used to be a 1, now it's a 2. The vertical distance from here to here was a 4, now it's an 8. So it is taller. It looks skinny, it's not, it's taller. Yeah.
Can you just multiply the y's from the original function and just find the y's of the norm?
Well, what you would do is you would multiply the y's by 2 and then subtract 4. So here's, for example, this y value was a 4, right? Right? Okay, double it. Now it's an 8. Subtract 4, now it's a 4. Hop, there it is. And same thing for this one. This one was a 1. Double it. Now it's a 2. 2 minus 4 is negative 2. There it is. So yeah, you could just manipulate the coordinates that way. Okay. Questions, comments, concerns on how to describe transformations or how to graph quadratics? Sir. I don't think they'll count the word shift as wrong. I think that that's okay. You do need to say vertical or horizontal, and they're not going to be looking for words like up, down, left, right. But you should be okay writing shift instead of translate. Yeah, you should be okay with that. Horizontal shift of -3. That should be fine. I don't think they're picky about that. Now, these 2 down here are not quadratics, they are cubics. But they're still in what looks like vertex form. Now, these aren't vertex form because cubics don't have a vertex. Do you know what cubics have? They have an inflection point. So if you wanted to, you could call this inflection point form. Nobody does. But that's what it finds. What makes the inside equal 0, comma the number to the far right? That's going to find the inflection point. Not all cubics can be written in this format. The only ones that can be written like this are ones that are symmetric around their inflection point. Are all cubics symmetric around their inflection point? Now that I've said that? Yes, they are. But they can't all be written like this. So I need to amend what I said. Only cubics can be written in this format are, I believe, ones that they don't do this, I think. They don't have this like up then down situation going. I believe cubics that are written in this format will always look like this. They don't have these maximums and minimums. And I'm recording that and putting it on YouTube, so hopefully I'm not wildly wrong. So I'm pretty sure that that's how that works out. Now, check this out. I was going to use that piece of paper anyway, so check this out. This would appear as though there are 2 horizontal transformations. And the reason why is because x is negative. In fact, the inside of this is kind of written in a weird order, isn't it? What I'm about to do, I am only doing because it makes it easier to graph. And it makes it easier to describe transformations. You don't have to do what I'm about to do, but it is a really neat skill to have. First thing I'm going to do is I'm going to change the order of the argument. Written in this order, you could easily follow SADMEP on the inside and describe those 2 transformations. You could say horizontal translation of -2, which we all know means left 2 units, then reflect over the y-axis. So if you shift left 2 units and then reflect over the y-axis, it puts you at +2, right? Doesn't it have the net result is just shifting to the right too? It does, doesn't it? Watch this. I factored the argument. I factored a -1 off of the negative x plus 2. It's still within the argument. I mean, I'm hoping we can all see that if you distribute this -1, you get this. And the exponent's still on the outside, yes? This is a product, though. And in Algebra 1, you learned that when you have a product raised to a power, you can actually treat that as both objects raised to that power. I'm going to stop writing h of x because I'm running out of horizontal space. I'm just going to write equals. And what's -1 cubed? -1. This does not have two horizontal transformations. This does. Now they're the same graph. But when describing two horizontal transformations, if you can avoid it, I say avoid it. Yeah.
Can you explain how the -1 is able to become, like, how its own cubed thing?
Because of this property. AB to the, I don't know, exponent of m. Because this is a product, not because it's not multiplication, or since it's not addition or subtraction. Because it's a product, that's the same thing as saying a to the m times b to the m. Just like that. It's just an exponent rule.
Oh, so you put the brackets there just to show that.
I put the brackets there so I didn't see parentheses.
Okay.
That was the only, they mean the same thing. It just looks better.
Okay, got it.
And that's why I stopped writing them once I didn't have parentheses inside of something. That was why. So yeah, so I just raised each piece of the product to the third power, and look at that. Much easier to look at, much easier to describe in transformations than this is. That's the only reason why I did it. Now, someone last period said, well, couldn't you just pull this -1 from in here to out here, just like you're factoring it? And I said, no, you can't just pull it from the inside to the outside. You can't do that. And they said, why? And I said, well, because what if it wasn't a quadratic, or what if it was a quadratic instead of a cubic? What if it said this? And now we try to do what I did before. Oops, this is -x plus 2. Sorry, forgot to do that. So factor out the -1 from here and you get this. But when you square that -1 on the front, -1 squared is +1. So no, you can't just factor the GCF out to the front like that. You can't do that. Okay? You have to respect the exponent rule first. And that can also come in handy for you. For example, it could have said this. It could have said this. I'm just making up a new quadratic now. Okay? This looks like two horizontal transformations, doesn't it? But you could do this. Square this and square that. So you'd have this quadratic now, which only has one horizontal transformation. So it's a useful skill because it makes describing transformations easier, and it also makes graphing, especially for quadratics, much easier. But that's why I did it here. So what's the description? Multiplier on the front has to be described before the addition subtraction because PEMDAS, right? Vertical outside same. This is reflect over x-axis. Vertical shift, vertical translation, whatever you want to say, -1. I wrote shift because I don't have a lot of space. And then this one, horizontal shift, 2 units. Horizontal, inside, opposite. Remember, so it looks like you're subtracting 2 from x's. You're not. You're adding 2 to your x's. Means shift right 2. Horizontal shift, 2 units. This is a cubic. Oops, pointed at the wrong thing. This is a cubic whose inflection point is at 2, -1. That's here. And instead of going like this, like a standard positive cubic would, since it's a negative cubic, it's upside down. So it does this. Where exactly? I don't know. If you want to plug in some values and find out, we can. Let's substitute in x equals 3. 3 minus 2. Oh, crap. A whole bunch of hands just went up. What did I do wrong?
Where does the reflect over x-axis come?
Well, what would have made the inside of this equal 0? 2. So the inflection point is still 2, -1, right? Okay. The description of this one is shift left 2, reflect over y-axis, shift down 1. The description of this one is reflect over x-axis, which turns the graph upside down. But y equals x cubed is an odd function. That means reflecting over the x looks exactly the same as reflecting over the y. So that's where that transformation, that's why we can say that we can interchange those two. Is this an odd function? No, but x cubed is an odd function. So if there's a reflecting over y-axis, there's a way to manipulate it so that the equation actually says it's a reflection of the x-axis. That's going to be true for all cubics. This is the reflect over x-axis. Okay? Yep.
If you reflect it over the x-axis, would it be at
So the reason why it's still here at -1 is because the reflection happens before the shift. That's why. Okay? Yes?
Is factoring the only way you can tell if it's
A negative. So would I have said that this? Would I have just looked at this and said, "Oh yeah, it's been reflected over the x-axis"? No, I would have said that it's been reflected over the y-axis. But again, this is what it looks like when it's positive, right? And this is an odd function. If this is 0, 0, this is an odd function. Reflecting it over the x turns that graph upside down and makes it look like this. But reflecting it over the y makes it turn left and right, which makes it look like this. So it's the same image. Well, we're just going to plug in points and just see what the picture looks like. So what makes the inside equal 0, comma this number, so 2, comma -1. I'm going to plug in 3. 3 minus 2 is 1. 1 cubed is 1 times -1. So I have -1 minus 1. That's -2. So 3, comma -2 is here. And because this is its inflection point, I'm guaranteed that the next coordinate to the left would have been right there. Guaranteed, because that's its inflection point. So it's going to be symmetric around it. And the graph will do this. I mean, I don't know exactly where it crosses the y-axis. That's just a quick sketch. But it's going to look something like that. So as you can see, it looks like this. You could either say it's upside down or you could say it's left-right. It doesn't matter. Either way, it didn't do what a standard positive cubic would have done. Its orientation is wrong. We don't need to do any kind of factoring anything here because there's only one horizontal transformation. But look, it's got this negative on the front. That means it's going to be shaped like this again, because you can say it's upside down. I don't need to I don't want to write the words for the transformations, but reflect over x. Screw it. Let's just write it. Those are 3 different vertical transformations. That negative on the symbol, that negative symbol on the front is its own transformation. That is reflect over the x-axis. Or you can say reflect in the x-axis. Either one. They mean the same thing. Multipliers, don't worry about the negative symbol. Multipliers are always a dilation. Since this is outside, it's vertical. Vertical outside, same. Vertical dilation, factor 1/2. And then this last one, vertical shift, 2 units. Horizontal, inside, opposite. Looks like you're subtracting 3 from the x's. You're not. You're adding 3. That makes them bigger. Horizontal shift, 2 units. That means shift right 2. Let us graph. The inflection point, what makes the inside equal 0, the number to the far right is 3, 2. Yes? It would be 3, not 2. And I even put a 3 right there. 3 units, thanks. I looked over here when I was writing. Horizontal shift, 3 units. Maybe. Now, if you don't mind graphing decimals, then just go 1 to the right to x equals 4. If you don't like graphing decimals, the trick that works because of transformations is, see this denominator? It's telling you how far left or right to go if you would like to avoid graphing decimals. So if we go 2 to the right of this dot, we will not have to graph a decimal. So the next x is 5. 5 minus 3 is 2. 2 cubed is 8. Half of 8 is 4, but make it negative. Negative 4. Negative 4 plus 2 is negative 2. So 5 comma negative 2. And since they are symmetric, instead of going right 2, I'll go left 2. And instead of going down 1, 2, 3, 4, I can go up 1, 2, 3, 4. It'll put me right there. See, this is right 2, down 4, so go left 2, up 4, because they're symmetric around their inflection points. Or you could just plug in x equals 1. You'll get 6 if you do it. Like that. Okay, next. It says use a graphing utility to explore these transformations. Okay, no, I don't want to do that. Instead, what we're going to do is we're just going to talk about what's going to happen. Let's do f of 2x. That means where you used to have an x, you're going to stick a 2x. Horizontal inside opposite. This is a horizontal dilation, factor 1/2. Or, because this thing's vertex is at 0, 0, we could square this 2 and this x and get this, which is a vertical dilation of factor 4. They're the exact same thing because x squared's vertex is at 0, 0. They're the exact same thing. Is it always true? No. It's true for x squared because its vertex is at 0, 0. It's October. We'll do orange and purple. F of 1/2 x. That says where you used to have an x, drop in a 1/2. Looks like this. Horizontal dilation. Factor 2. Remember, you have to use the reciprocal. Or you could square the 1/2 and square the x. 1/2 squared, 1/2 times 1/2 is 1/4. Vertical dilation, factor 1/4. Completely up to you. And this would have just showed you that these two graphs are actually the same. And this would have showed you that these two graphs are actually the same. It's kind of a waste of our time to put it on a graphing calculator because you all already saw me do that on this paper. Questions, comments, concerns on how HIOVAS is working and things like that. How to sketch a cubic, sketch a quadratic, describe transformations, any of that? Yes?
So for a cubic, it's automatically it's going to reflect over the y-axis? Or
What is, if you see a reflection?
like x to the
Well, it doesn't matter which one. Here, I'll put that on. I'll just. So I'm going to do x to the x cubed, okay? X raised to the third. Zoom 6. So here's y equals x to the third. Whee! There it is, okay? Now, if we were to say -1 times x raised to the third, that is an outside change. So let's think of it as a vertical reflection. This is reflecting over the x-axis. This is going to turn my graph upside down. And it should be in red. Ready? Graph is upside down in red. Correct? Reflected over x-axis. But if I did this, let's do green because that'll show up nice. Because it's on the inside, now it's a horizontal reflection. That's reflecting over the y-axis. Now watch where it draws this green graph. Did you see the red change to green? It did. That's why I was trying to change the color so you would see that happen. But the red graph turned green because it's the exact same graph. Because x to the third is an odd function, reflecting over the x-axis is exactly the same as reflecting over the y-axis. Okay?
So x to the third will never reflect over the y-axis?
No, you can describe it as either one reflecting over the x or reflecting over the y. It doesn't matter. I chose to not ever have two horizontal transformations if I could avoid it. That's all I was doing. I was trying to avoid two horizontal transformations. Because then you have to remember SAD/MEP. And it makes it difficult to graph. Like, let's one more example. What if I gave you this and I told you to graph this? It kind of sucks, doesn't it? But you could do this. You could cube that 2. And now it's not so bad. And it looks a lot nicer. And now it's more obvious where your inflection point is, 2, 1. And if you ask me what this graph looks like, I'd be like, well, okay, I can see its inflection point, 2, 1. It's going to look narrow. This, I go 2, 1, and it looks tall. So it's going to do this. It's like instant because I recognize vertical stretch much faster than I recognize horizontal shrink, especially after some kind of weird shift. You know, I know the graph looks like this in a heartbeat when it's written that way. Okay? Yep.
Why'd you do 2 graphs for the cubics?
Why did I do 2?
Yeah.
I didn't.
No, for the cubics, not the.
You mean for the quadratics? Why didn't I do 2?
Oh, no, why did you?
Why did I do 2 for the quadratics?
Oh, yeah.
These are quadratics.
Okay.
I just forgot to do it for the cubics.
Oh, okay.
I just wanted you to see what the parent would have looked like. I guess we could do that real quick. There. I just went, because it goes 1, 1, and negative 1, negative 1, 0, 0. Okay. I feel like we have beat the crap out of that dead horse. Let's see. What's next? Oh, fun. It says the graph of f of x can be drawn by connecting these points. Boop, 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 boop. These 5 points right here. Part A says plot these 5 points and connect the dots. So we're going to plot these 5 points. I can't keep all of them on the screen while the grid is on the screen, so you'll just have to look at your own papers, but there it is. Yeah, let's do blue. Negative 4, comma, negative 2 is here. Negative 2, comma, 3 is up here. Negative 1, 0, back down. 1, 4, eek, way up here. And 4, 2. And then we're supposed to connect those with straight lines to the best of our ability. Close enough. There it is. So we've done part A. We have sketched f of x. You notice that we have some space down here? What we're going to do in this space is we're going to describe the transformations we see, and then next to that, I'm going to write what that does to the x and y values. And I'll even keep the same color scheme that I was using before. Vertical outside same feels green today, so I'm using green for vertical. There are 3 vertical transformations. The negative sign is its own transformation. Outside, same. Vertical outside, same. You have to go in the same order that you would expect, which means follow PEMDAS. Multiplications have to happen first. These are both multiplications, so it actually doesn't matter which one you describe first. That's unimportant. I'll just go left to right. So reflect over x-axis. And then there's a 2. Whenever you put a number next to something in mathematics, you're multiplying. And it's vertical, so it's a vertical dilation. All dilations are multiplications. Vertical dilation factor 2. But those 2 transformations, what do they do to the values of y? Algebraically, arithmetically. What am I doing to the values, my y values? You're multiplying, but what are you multiplying by? Negative 2, yeah. So this just means multiply y by negative 2. Yeah, but I just meant like make it easy. You were describing again. But as far as the numbers are concerned, just multiply by negative 2. Call it a day. Okay. Now this one, vertical shift or vertical translation, whichever word you want to say, 4 units. Vertical outside, same. You know what that's doing to your y value? It's adding 4. It's literally doing what it looks like. So let's go down to our table now before we do that one. And let's multiply our y value by -2 and then add 4 to it. I forgot to write the number 4. Literally, -2 times the y value and then add 4. These are the y values. -2 times -2 is 4, plus 4, 8. -2 times 3 is 6, plus -6, excuse me. -6 plus 4, -2. -2 times 0, 0. Plus 4, 4. -2 times 4 is -8. Plus 4 is -4. -2 times 2 is -4. Plus 4 is 0. There. I have my transformed y values. Like I said, I'm using the same color scheme. This right here. Horizontal shift. Horizontal inside opposite. 3 units. Looks like you're subtracting 3. You're not. You're adding 3. That one's easy. You just add 3 to your x values. These are your x values on the left-hand column. -4 plus 3 is -1. -2 plus 3 is 1. -1 plus 3 is 2. 1 plus 3 is 4. 4 plus 3 is 7. We have our new ordered pairs. And I had no way of knowing what this thing would have looked like. That's what, 4 transformations? I can't do 4 transformations in my head. But I can affect my numbers that way and plot them. -1, 8. 1, -2. 2, 4. 4, -4. 7, 0. Woo! She's crazy, nerds.